Welcome back. So it's time to eat. Let's talk about forks. So we're not talking about this type of fork which looks quite uncomfortable to use. We're rather speaking about mining and forks, blockchain forks. So what is a fork, and when does a fork occur? So if you think of this network here, network structure, right? You have on the left side, you have this miner that's propagating a block. It takes some time to reach the other miners, and in the meantime, this miner here might find a competing block, a red one, which then also propagating in the network. And at this point in time, we have a partition because some of the nodes have the green blocks, some of the nodes have the red block. And there might be even a third block coming from the topmost miner here. So now we have three competing blocks that are propagating the network at the same blockchain height, and only one can win. So in that particular setting, we see there's a network partition, and people are basically losing their efforts because only one of them can win. So let's assume here that the green block will win. Then the red and the orange and the yellow one are invalidated, and these are stale blocks because they have lost efforts. So this is what happens when there are like forks or stale blocks, and because you have now, instead of having one unified network, you have like 1, 2, 3 sub-networks, which are each weaker than if they were to collude and work together towards a unified chain. And therefore an adversary, which is a third party here, could have an easier game at performing, for example, selfish mining, an attack that we will be looking in the security lecture, denial of service, and double spending. So forks are not good, right? So fights generally are not good. They're compartmentalizing, they're making a few entities weaker than necessary. It would be better if they combine their forces and work together. So on the visual front, you can visualize a fork really simply by something like this. So you have two blocks, B1 and B1 prime, and B1 prime might outrun the block B1 and become the main chain. So B1 did now die. It's a stale block. It's no longer the main chain. And then you have the length of the chain here to be until B3. Now, this is a stale block, right? Stale in the sense that it's not part of the main chain. And the main chain, which is this part here, it's defined by the length in terms of number of blocks plus the difficulty, right? It's very important. Like, the difficulty plays an important role in the longest chain rule. The consensus is that the main chain is the longest chain with the most proof of work. And the proof of work difficulty measures how much work there has been done. And that's why it's very important to consider the length plus the difficulty. So what types of fork exist? Well, there are quite a few forks. So for example, you can update the protocol from P to P prime, right? You can change the validity set from an old P to a new P. And then you have a difference N, which is between V and V prime. To change a blockchain, you can propose so-called improvement proposals, which exist for Bitcoin, Ethereum, and many other projects and chains. And these are typically then discussed in the community board and ripped apart. I'm joking. Typically very constructive discussions where you can also learn a lot from very smart people working on these protocols. So here just a few examples of Ethereum improvement proposals that you can look at. And you can see here the status of them is final. You can see which layer they're at, and you can see which co-author these proposals. So maybe you've heard about a hard fork. Let's go into the specifics of what a hard fork is. So a hard fork makes a previously invalid block or transaction valid or invalid. And all nodes must upgrade to the latest version in order to accept this, in order to be able to operate on that new hard fork, right? So here, once you follow the new rules, right, you find the old rules to be wrong. Basically, blocks that are built according to the old rules are no longer valid in the new world, right? In the new world, where you do where you perform the hard work, non-upgraded nodes reject the new rules, and upgraded nodes reject the old rules, possibly. So this is kind of diverging or forking the chain. So a hard fork example is, for example, when the Ethereum blockchain was forked because a smart contract vulnerability was exploited. This was on the DAO, and the fork was later reversed through. The fork basically reversed the hack in a sense, right? So it changed the course of the past of a blockchain, and this is something that shouldn't really be happening because the blockchain was no longer append only at the time. So this was quite controversial in the history of Ethereum, and this is also where the power of centralization in the community management might become a problem. If like a few single individual can convince a sufficient set of miners to follow a certain block. So that's something that happened. I think it was a great exercise, and everybody learned a lot of things from those events. Now, a soft fork is where only previously valid blocks or transactions are made invalid, right? So this is kind of reducing the functionality. So you want to remain backward compatible, so old node still accept new blocks as valid when you go forward, but they don't understand this newly introduced functionality. Like, for example, merged mining is kind of a soft fork because you add some functionality. The old nodes, they don't have to update. They don't understand what you have inserted into this Coinbase input, but they don't care, right? And then there are different ways to activate soft fork. You can have a majority of miners that upgrade to enforce a soft fork, or you can have the full nodes so the non-mining full nodes that broadcast transactions in a network to enforce rules without the miners. So that's quite interesting because so far we've only discussed that miners are actually those with the real power in the network, whereas with user-activated soft fork, the non-miners actually also do have quite some leverage here, which is very encouraging, I find. To give you a few examples, so for example, if you make a transaction invalid that is bigger than 1 kilobyte, that would be a soft fork, right? Because you now make smaller transactions, so the old nodes are still happy to accept those transactions. So pay-to-script hash can also be a soft fork. So if you send the transactions to a script hash, right, those addresses that start with a 3, instead of a public key hash, those that start with a 1. So the recipient must then provide a script which matches the script hash and input data to make the script evaluate to true, such that the transaction is valid. Otherwise, if it doesn't evaluate to true, it would not be valid. So these are examples of soft forks, or of how you can kind of restrain the rules. The old nodes will still accept the input. So summarizing, you can think of the types of fork as such here, right? You have expanding forks, you have reducing forks, you have conflicting forks, and you have conditionally reducing forks. And these are just a few examples. We don't have to really go into the details, but what's interesting is if you expand, this cannot be a soft fork, right? If you expand it, it quite needs to be a hard fork. Segregated witness is an example of a kind of a fork, right? Where you have here the signatures of a transactions were malleable before, right? They can change while remaining valid. So you can flip a few bits in the signatures, but the signature itself still is a valid signature according to a public key. So what SegWit did is to separate the transaction signature from the transaction data. The transaction signature represents roughly 65% of the data of a transaction. Now, the advantage of segregated witness is that it increases the number of transactions that can be stored in a block without technically increasing the block size, and it does remove transaction malleability because the transaction no longer is part of the content in the block. Well, the disadvantage is that signatures are required to validate a block, and because you have to get them somehow, right? So you basically must get the signatures from somewhere to validate a block, and the design of this construct is quite complex. So how can you vote through blocks, right? If you want to perform a fork, you might want to ask the community, so should we decide to work on this particular block or not? Well, as I mentioned before, right, you can write a Bitcoin improvement proposal or an improvement proposal. This can then be discussed, it can be implemented, and then it can be voted by miners. What's interesting is people like to use the Coinbase transaction data field, and miners can then vote, for example, over the last 100 blocks. And if the majority, like more than 55% of miners agree by voting in the Coinbase transaction with the hashing power, then this can be implemented. That's kind of a consensus on the community side of how to proceed. Thank you very much for watching. This was on forks.